like a map with no ocean.
Okay, so problem number 2. What we're given is the following vector field. So f arrow is equal to x squared, comma, x squared. Okay, and our given curve is y equals x squared. This is what it's bound by. So y equals x squared and y equals x as x goes from 0 to 1. Okay, so 0 to 1. So let's draw out, well, first of all, also, that would be nice to, it'd be good for me to tell you guys what we're actually trying to do in this problem. So we're calculating the line integral over the closed curve, which is c, of f dot t ds. Okay, so this is just the line integral over c. All right, so the curve, let's look at what it says. So we have our x and our y, all right, and let's say here's 1, and here's 1 here. So this is 1, 1, and this is 0. So if the curve is made of two separate functions, what we have is they intersect at 0 and 1. So this is the y equals x line, and this will be the y equals x squared. Okay, so this is our curve here, and they said it is oriented counterclockwise, so it means it's going this way, right? It's going around like that. Okay, so everything in the middle here is our domain, and the boundary of the domain is C, which consists of both of these functions. Okay, so it's like the fencing around it. All right, so first option, we could compute this directly, and in which case we would have to use separate parameterizations for each graph, right? This one and this one, so we'd have to compute them separately and then add them together, etc., etc. But now that we have the tool of Green's theorem in our toolbox, that makes everything a whole lot more simple, in a way. It's handy to use sometimes. So basically, Green's theorem says that this is equal to, again, the double integral over the domain itself of partial f2 partial x minus partial f1 partial y, and then dA, okay? So in this case, what we could do, so f sub 1 and f sub 2 are actually the same thing, but it is going to be different because we're taking the partial derivatives with respect to different variables, so it won't turn out to be 0 necessarily. So if we do this, we take the partial with respect to x of the second component, which is x squared, and then we subtract partial with respect to y of the first component, which is also x squared. Okay, so what this turns out to be is a 2x minus 0. So that is not 0. It's just 2x. Okay, I messed up that x. 2x just by itself. Okay, so this is what we're going to plug into the parenthesis area here. So that is 2x. And we have to figure out what are the bounds for this domain here. So we're going back to the beginning of the course, kind of, and we're going to make this a vertically simple region. Remember that? Vertically simple and horizontally simple? Technically, this could be both, but I don't really want to work with square root things, so this is good. If we do vertically simple, that means x is just bound by 2 constants, and our y is bound by 2 functions of x. So on the bottom, y can't go below x squared, and it can't go above x. Okay, the line y equals x. So these are our bounds, and now we can set up our integral, our double integral. So we have x going from 0 to 1, and y going from x squared up to x. Our integrand is 2x. Oh, 2x. There we go. 2x, and we have it in the form dy in the inner and dx. Okay. All right. So now let's just compute from here. So we're calculating the inner integral. So we have 0 to 1, and then if we are integrating with respect to y, we get 2xy as y goes from x squared up to x. Okay, so that's what we get there. And then when we plug them in, we get 0 to 1, and then 2x times x minus x squared, okay, and then a dx there. So this turns out to be, I'll bring the 2 outside just so we don't have to deal with it. So 2 times the integral from 0 to 1 of x squared minus x to the third, and then a dx. So we'll just integrate simply. Single variable calculus. Doesn't this feel good? Single variable. Yay. When things were simple. But, you know, good times. So when we integrate, we get 1 over 3 x to the third minus 1 over 4 x to the fourth. And x is going from 0 up to 1. So when we plug this in, we get 2 times 1 over 3 times 1 to the third, which is just 1, minus 1 over 4, and then minus a 0. So this turns out to be a 2 times 4 over 12 and a 3 over 12. So that's 2 times 1 over 6, right? Or 1 over 12, sorry. 2 times 1 over 12, which is 2 over 12. Which turns out to be ultimately 1 over 6. I was just trying to save space there at the end. So yeah, that's our answer. And you would have gotten the same thing from calculating the direct line integral over these 2 separate boundary curves. Okay? So this is our answer. And yay, happiness. Okay. Alright, so that does it for the practice problems video. I hope that helps. And I'll talk to you guys later if you watch future videos.
There's a limit to your care. So carelessly there.